before I go ahead and talk about my work, I should acknowledge the people who actually did the work. So this is my group at the Bangalore, and most of the people which you see who has already graduated, several of them including Tribhuvan and George. So Tribhuvan was my graduate student who is now at ORNL, and George was a UG student from IISc, and now currently he is a student at Columbia, Missouri. And these are the two people who did most of the work, and the work which I will show are mostly done on our SERC Craig cluster, which is India's fastest supercomputer. Also, we have a humble cluster in our own group, which we call Tage and Planck. Here are the funding agencies which has generously funded us to carry out this work. So as you all know, most of the heat which we generate gets lost in terms of the conversion losses, and this is of the order of 2/3 of the energy which you generate. So the idea is, if somehow we can tap into this energy, and this can be done if we can convert this thermal energy to something which is useful, essentially to convert it from thermal to electrical energy. And this job is done by a special class of material which is called thermoelectric through two kind of effect, namely Seebeck effect and Peltier effect. Seebeck effect, what it does, if you have a thermal gradient, it will give you the voltage, and vice versa is the Peltier effect, where you apply a voltage gradient to get the thermal gradient. Sorry. And so these are, as I showed you, they are devices. So they have efficiency. So they are essentially a Carnot type of an engine. And the efficiencies depends on this equations which I'm showing you. And this one you can easily recognize. This is a Carnot efficiency multiplied by this term, where the ZT, which is also called as a figure of merit, this is the term which depends on the materials property. As you know, I come from the Material Research Center. So we work mostly on the materials. And you can see that efficiency of this device, how it changes with the ZT. So you can see if you have a 1 and around 500 operational, the temperature difference between the hot and cold junction, if that is a 500, so your the conversion is less than about 12%. But as you keep on increasing, one can easily achieve to the order of, let's say, 2 or 3 ZT. If you reach, you can start converting to going to the 25% range. So this is what we like to do. And for 70 years nearly, most of the materials which were generated, they never were able to cross the 1. But last 5 to 10 years, there was great ideas which were explored, and through that, there are some materials which came out which gave us a ZT of the order of around this, above 2. And I'll tell you what are the ideas which went behind creating those materials. So here is the expression for ZT, and it is directly proportional to electrical conductivity, Seebeck coefficient, or thermopower, and inversely proportional to the total thermal conductivity, which include lattice as well as electronic part. So most of the thermoelectric materials are insulators or semiconductors. So the most dominant factor which defines the ZT is the lattice part of the thermal conductivity. Now, all of these physical quantities which you see in this equation, they all have a very funny relation among them. And to break this funny, to optimize the ZT, you have to somehow break or optimize. It's a great optimization problem. It looks very simple equation, but it's very complicated if we like to increase the ZT. For example, even sigma and S has an inverse dependence. So if you are in a range which is a semiconductor, then as you know, conductivity will be 0. But the thermopower or Seebeck coefficient is going to be very high. But overall, the product of these two, which is essentially also known as power factor, will be very, very low. And that means the ZT will be low. Now, if you go to the other extreme, which is a metal, of course, the conductivity can be very high, but the S is going to be close to 0. And then again, the product is also going to 0. But in between, this is the the region where most of the thermoelectric material lies, which belongs to heavily doped semiconductor or narrow band gap semiconductors. Sorry. Okay. So doing the, I don't know, it doesn't work. This battery is low. All right, so how to identify a suitable semiconductor is the first challenge. And since I do density functional theory calculations, so first thing which I get from any calculation is the density of a state. And if you look at the density of a state, you would come across various different kind of density state, but you can quickly look for certain feature, and then you can tell whether it's going to be a good thermoelectric material or not. And one of them is looking at the slopes of the density state near the Fermi energy. If it has a very large slope, for example, this case, through the Mott formula, you can see that dNE over D is going to be very large, therefore it will give you a large S. At the same time, large electrical conductivity, because it has a finite density of states near the Fermi energy. Whereas you come across a density of states which looks like this, where there is not so much changes, or things are not changing interestingly around EF, these materials will not give you a very good thermoelectric performance. So another point is, like I told you, the numerator was product of S square sigma. And these, you can maximize it if you have rather than a single band type of a structure where your band structure has just one parabola or one conduction band or one valence band. Unlike that, if you have a material which has a large number of electron or hole pockets which are given here, then you would sum it over across them and you can maximize it. Another point which you can look at it is S is maximum if the bands are heavier, and sigma is maximum if the bands are lighter. So if you have a combination of heavy and light bands, you can again increase the thermal conductivity. Okay, so this was about the numerator. Now about the denominator, that is the lattice part of thermal conductivity. You could look for a couple of things, because lattice part of thermal conductivity calculation, it was very challenging. It was not possible until recently. Even now, it's very, very expensive calculation. So you would like to know about it before you go on and do those expensive calculations. And that you can do by simply looking at the phonon dispersion relation, which slope can tell you about the group velocities. And the lattice part of thermal conductivity is directly proportional to the group velocity. So it should have a low group velocity, because you want a lower lattice part of thermal conductivity. And softer lattices, so if you remember, Professor Dev was showing his phonon dispersion where there was a phonon softening. That means the thermal conductivity is decreasing. So if we have a softer lattice, we can decrease the thermal conductivity. However, there is a challenge. If you have a soft lattice, then your melting point can go down. And as you saw, all the thermoelectric action happens at higher temperature. So your material should not melt before it becomes a good thermoelectric. I think it's doing okay. Okay, you can change it. I will continue. This one will. Okay, thank you. So here's the outline of my talk. I will tell you the three stories, or essentially three approaches, which we have recently developed, or in fact, it was developed in the community, but many of them are our original ideas. And if time permits, I will go through all three of them. Otherwise, I will conclude as far as I can go. So first one, the idea is, how do we scatter phonons but not electron? Okay, so this is what is called phonon glass and electron crystal. And so we have to look for the materials where we can get these two properties simultaneously. And one of such material is the Zintal phases. I don't know many of you are aware of this or not. It's a very interesting class of material which has cations coming from alkali or alkaline earth metal atoms. And an ion can be a single element, or it can be a complex. And what happens, it just doesn't work. Okay. So in this compound, the cation gives completely one electron to the anions, and they start behaving like a silicon. So for example, if you take a thallium, which was the first Zintal compound, this is here, and sodium thallium. So that was the first. So sodium gives one electron to thallium, and thallium starts start acting like a silicon. And because it got 14 electrons, and it forms a tetrahedral network of the thallium itself, and the sodium goes in between. So the structure becomes very interesting. Here is the structure. So sodiums are hanging there. So they work as a scatterer or as a rattler for the phonons, and the electrons can go through the lattice of the thallium. And but what we have looked at, so here are some of the interesting thermoelectric materials which are here. In which you could see that, like zinc antimonide is also Zn3Sb4. These are the Zintal materials, and they have shown a good thermoelectric properties. So what we have looked at, the cadmium-based thermoelectric materials, and you can see that the cation, anion part was a complex, which can be cadmium 2 antimony 2, or starting with just antimony 2, and A2 plus is the cadmium ions. So we try to look for if this material has the electron gas, electron crystal and phonon gas. So here is we systematically looked at the cadmium antimonide, calcium cadmium 2 antimonide, strontium and barium cadmium 2 antimonide, and you can look at that. You got several pockets, okay, for the electrons as well as hole. Of course, this has a parabolic bands, but still it has these flat bands here and the mixture of flat and highly dispersive band. So all of them, if we look carefully, their band structure, we start to see the features which I just told you 3 slides back. So we did the transport calculation, and we found, as expected, they all have a large conductivity. So there will be a convention in my talk which will be followed. All the dotted one is for the P-type, and the solid one, dotted one for the N-type, and solid is for the P-type conductivity. And so these all have a large electrical conductivity, which is good. That's what we wanted. And if you look at their Z-back coefficient, most of them, so there is a bipolar effect like here, at some temperature, the minority carrier also start participating. So majority carrier has one kind of a sign, and minority carrier has another kind of a sign, and they start canceling. And then it leads to a peak here. So for many of the materials, it's more or less very much free of the bipolar effect. And if we look at the product of them, we start to get a very large number of power factor. So we started to see a good numerator part. And when we compare it, now let's look at that, how good they are compared to some of the state-of-the-art thermoelectric material. And what you would find that at a reasonable range of electrical conductivity, we can get a very high value of S. And sometimes it is better than lead selenide or even lead telluride. So these materials looks to be very promising, or better than some of the so electron crystal part is satisfied. How about the phonon part, or the denominator part? So here is the thermal conductivity which we calculated here, and you could see that the thermal conductivity is quite low. It's below 1 watt per meter Kelvin, beyond 500 centigrade for most of them, except for the strontium cadmium antimonide, where it is slightly high, but it's still quite low. And the order which it follows is following. Strontium has the largest, then calcium, and then cadmium antimonide and barium. So this was puzzling us why it is like this, because if we look at this, just the group velocity, as I told you, what are the markers which you can see for the phonon transport and for the electron transport, and I told you group velocity was one of them. But here it doesn't work like that, because if you look at the group velocities, actually, you will find that this should be the order. Calcium cadmium antimonide has the lowest, highest group velocity, so it should have a highest thermal conductivity, but that is not the case. Okay, so we have to understand why. And so, as you know, the thermal conductivity happens, or because of the enharmonicity of the crystals. It's not a harmonic property.